All right, let's jump right in, because today we're pulling back the curtain on a little secret from Einstein's world, and it's hidden in something you probably use every single day: your car's speedometer. It seems so simple, right? But what it's actually measuring is going to completely change how you think about your daily drive and maybe time itself.
So, let me ask you a question. Next time you're driving, when you glance down at that dashboard and see the needle pointing to, 60 miles per hour, what is that number really telling you? The common sense answer you're thinking of? Well, that's not even half the story.
Now, you'd think your car is measuring what physicists call coordinate velocity. You know, the classic distance over time that we all learned in school, the one with a hard cosmic speed limit, the speed of light. But nope, get this. It's actually measuring something called proper velocity. And the wild part about proper velocity, it has absolutely no upper speed limit. To wrap our heads around how that's even possible, we need to completely rethink our idea of time.
And that's where we'll start. The whole secret to your speedometer isn't about how we measure distance. It's all about how we measure time. See, it turns out our universe is basically running on two fundamentally different kinds of clocks.
On the one hand, you've got global time. You can think of this as the map clock. It's that old school idea of one giant, universal clock for the whole cosmos, ticking away at the exact same rate for everyone everywhere. But then, relativity comes along and gives us proper time, which is the traveler's clock. This is the time on your personal wristwatch. And here's where it gets mind-bending. Your clock can and does tick at a different rate than everybody else's.
And let's be super clear here. Proper time isn't some vague metaphor. It's your literal, physical, personal experience of how time passes. When you're moving, your clock is ticking just for you. And this personal clock, well, it's the master key to understanding what's really going on when you hit the gas pedal.
Okay, so we've got two different kinds of time. And if you have two kinds of time, well, it stands to reason you're going to have two kinds of velocity, right? It all just boils down to one simple question. Which clock are you paying attention to? The big one on the map or the one on your wrist?
So here's how it breaks down. Coordinate velocity, we'll call it v, is the distance you travel divided by the time on that universal map clock. Simple enough? But proper velocity, w, is that same exact distance divided by the time on your traveler's clock. See the difference? The distance is the same, but the time is personal. And that one little change, it changes absolutely everything.
And listen, this isn't just some wacky thought experiment. It's a fact. As physicist P. Frondorf puts it, this is literally what your car is built to do. It measures the distance you've driven on the road, divided by the ticks of your own personal time. Your everyday car is a real-world relativity machine.
So why does this even matter? What's so special about proper velocity? Well, for starters, because your personal time slows down the faster you go, your proper velocity can just keep climbing and climbing with no speed limit. It's also more fundamental. It's directly connected to an object's momentum. And maybe most importantly, it's what's called synchrony-free. That's a fancy way of saying you don't have to worry about syncing up clocks across huge distances, which is a massive headache saver in physics.
Okay, so speed is more personal than we thought. Got it. But what about the forces we feel when we're driving? You know, that pushback into your seat when you accelerate, or the pull to the side in a sharp turn. Well, believe it or not, that story gets even stranger. Let's talk about what the source calls accelerometer invisible forces.
You might want to brace yourself for this one. Some of the most common forces that you experience every single day aren't really a push or a pull in the traditional sense. They're more like phantom forces, illusions that are created by the very shape and fabric of space-time around you.
And we are talking about feelings you know intimately. That force that presses you into your seat when a plane takes off, that's a geometric force. That feeling of being pulled outward on a merry-go-round, also a geometric force. And the most famous, most powerful one of them all? Gravity. Yep, that's one too.
So what makes a force geometric? Well, for one, it acts on every single ounce of your body all at once. For another, it completely vanishes if you're in freefall, like an astronaut on the space station. And this is the really wild part. A sensitive instrument like an accelerometer, if it was moving with you, wouldn't even detect it. It's like the force is a ghost in the machine.
This leads to the million-dollar question, doesn't it? If gravity or inertia isn't a true force, like a punch or a shove, then what in the world is it? What fundamental property of the universe are we actually feeling?
The answer is honestly one of the most profound and beautiful ideas in all of physics. These so-called forces, they aren't connected to pushing or pulling at all. They're connected to the flow of time itself. Specifically, they are linked directly to this, the differential aging factor. And yes, you heard that right, aging.
And this is the moment that just changes everything. Because gravity is a geometric force, and because these forces are linked to differential aging, it means that right now, wherever you are, your head is aging just a tiny, tiny infinitesimal bit faster than your feet. It's a real physical effect. The force of gravity we feel is fundamentally our body experiencing time flowing at different rates across its own length. Just wow.
So let's bring this all home. This whole journey isn't just about collecting weird physics trivia. It's about actually adopting a more accurate and, frankly, a more powerful way of seeing the physical reality that we live in every single day.
There's this fantastic quote from the source material that just sums it all up perfectly. Relativity isn't some strange, exotic thing that only happens near black holes or in giant particle colliders. From your car's speedometer to the reason you feel weight, we are constantly living and breathing in a deeply relativistic world. So think about the shift in perspective we've made here. We've swapped out the old, comfortable idea of a universal map time for our own, personal traveler's time. We've traded a velocity that has a speed limit for a proper velocity that has no limit at all. And we've evolved from seeing forces as simple pushes and pulls to understanding them as geometric effects, tied to the very flow of aging.
And here's the big takeaway. This traveler-first way of looking at physics isn't just a different angle, it's a better one. It gives us a single, unified set of rules for motion that works just as well for a car driving down the street as it does for a beam of light screaming across the galaxy. It's a more complete picture of our universe. So, I'll leave you with this final thought to chew on. We've just seen that something as basic as the passage of time is actually personal and unique to each of us. It really makes you wonder, doesn't it? If we could be that off base about something so fundamental, what other hidden layers of reality are hiding right under our noses, just waiting to be discovered?